Alright, welcome back. Today we're going to talk about one of the most important theorems in all of calculus, the fundamental theorem of calculus. We're going to call this from now the FTC or the Sorry. So the fundamental theorem of calculus is how can we solve for area if we cannot use a geometric formula like we did in the last lesson. So let's review the last lesson though real quickly here. We have the graph below and they want us to use this to evaluate the following integrals. So these are, remember, what we call a definite integral because we're evaluating from 0 to 3. We have a number. So remember, a definite integral is going to have some sort of a to b, where the indefinite integral is not going to have anything right there. It's going to be blank spaces. So the first one says we want to find the area from 0 to 3 of our function. Now you got to be careful. You got to be really careful about this. Recall one of the most important thoughts that we talked about last unit is that this is a derivative. If I'm looking at this as a function, I can think of this as being a derivative graph right here. So we're saying anything above has a positive area and anything below has a negative area. And you want to be really careful with that because what they're telling us is that the area between 0 and 3 is 4, which is technically right. Area can't be negative, but we treat it like a negative. So we have to make sure that we are going to say that this is a negative 4. Just write it out. Because it's below the x-axis, this area we say is a negative 4. It does mean something for us in terms of our problems. So the area from 0 to 3 would be said to be negative 4 because this is below the x-axis. What this says for us, is that the change in f of x is negative. In the function is negative. It means our values are decreasing. And the area we're going to talk about later on tells us how much those values are decreasing by. Think sign charts, just like we did earlier. Now the next one says they want to find the area from 3 to 9. Well, that's easy. That's just going to be what they tell us is already above, so that's just going to be 7. And then they want to find the area from 0 to 9. Well, we're going to get this. Well, from 0 to 9, we have a break here. This is a critical number for us. That's 0. So we have a break there. So between 0 and 3, we know it's negative 4. And between 3 and 9, we know it was 7. And we add that, and we get 3. Now, in physics, we call this displacement. Does that sound familiar? We'll see that again. And now for number 4 says, this is all y's are positive. This is always positive y values. So whatever below the x-axis gets flipped. So we're taking the absolute value of the negative 4 plus the absolute value of the 7, those areas, and if we have them together, we get 11. Now in physics, we call this total, whoops, can't spell total distance. Does that sound familiar? We're going to see a lot of this year, so we're going to come back to those in a little bit. So let's go and get started with the fundamental theorem of calculus. This is going to allow us to be able to find the exact area between a function and the x-axis. And here's what it says. If a function is continuous on an interval, closed interval a to b, then the area is the following. Drum roll, please. F of b minus f of a. Now notice, this is the derivative. This is our antiderivative. So we have to take the antiderivative. There is our rule. That is the fundamental theorem of calculus. And we're going to use this a lot this year. And what it says is that the area under a curve, is the difference in the values between the values of f of x. And this becomes very important for physics, which we're going to see a lot over the next few weeks. So this should look a little familiar to you. If we've seen f of b minus f of a before. One, that was the top of a rock in the MBT, and we saw this when we did displacement with physics. Remember up here, that area is a displacement. We've seen this in displacement. So f is the antiderivative of f prime. That's a big thing to remember. Remember, inside the integral is my derivative, outside is my antiderivative, or the original function. So let's see how this works here real quick. These are very easy to do. You're going to ace this, I promise. So the first step, we are trying to find the area underneath the curve x squared plus 3. So if I were to just look at this, x squared plus 3 from 1 to 2. We want to find this area. We want to find that area. So to do that, my rule says take the antiderivative. So I can do this. I am going to get x cubed over 3 plus 3x plus c1. Don't forget your constant. Now, we're not going to write this we're going to see what happens in just a second. So, and I'm going to evaluate that. Now, there's a lot of ways to write this. We're going to evaluate that from 1 to 3. And now we're going to do the FTC step. The FTC step says to evaluate the function at 3 minus evaluate the function at 1. So when I plug in the 3, I'm going to use parentheses. Trust me, this is the coolest way to do it. It requires very little work. If I plug in 3, I'm going to get 27 over 3 plus 9. I can't really plug 3 in for C1, so I just leave that as C1. Minus, plug in the 1, 1/3, plus 3, plus C1. And let's see what happens here. If I distribute, I get 27/3 I know what you're thinking, Mr. Wernow, that was a 2. Let's change that to a 3. I just realized I made a mistake. So I'm going to fix my answer. So let's say this is 27/3 plus 9 plus C1 minus 1/3 minus 3 minus C1. So what do you notice happens? The C's cancel. In a definite integral, the C's cancel. Only in a definite integral the C's cancel. Therefore, we don't need them here. They will always cancel. If you want to write them down, you can. You don't have to. They'll cancel. And what I'm left with is, I don't know what this is, 27/3 plus 9 minus 1/3 minus 3. I'm just going to leave it alone. Okay? But if you're desperate, and it's just 16/3 if you want to simplify it. Right. Sorry about the 3. Should have been a 2, but, oh, that's not 16/3 anymore. Sorry, that was my original answer. I'm going to shut up now. All right, so for number 2, we've seen this before. We cannot have a product rule, so we have to distribute here. So let's see this. If I were to rewrite this, if I were to expand this, we would get 3x squared plus 6x minus 1, so plus 5x minus 2 dx. Don't forget your dx here. I can integrate this. This becomes 3x cubed over 3, or just x cubed, plus 5x squared over 2 minus 2x. Again, normally I would put a plus c, but in a definite integral they'll cancel, so I don't need to here. You can if you want. -1 to 4. And now we're going to do the most important step. We're going to evaluate the integral at 4 minus the integral at -1. And I want to see this for now. I want to see this for now because it's going to help you. Use big parentheses. And these don't take much. We're done. 4 cubed, 64, plus 5 times 16. I don't know what that is. That's what, 5 times 16? What's that? Oh, who knows? I think it's 80 over 2 minus 8. Plug in a -1. Be careful. -1. This becomes plus 5 halves plus 2. Don't simplify. You will spend more time simplifying this than you will just getting the answer, okay? And that's where we're stopping right there. So that's where we're going to stop our answer. So go to part 2. We'll take a look at a few more examples.